The title isn't really telling us. So the limit as x approaches c of some function f of x is equal to L. Right, that's the structure of a limit. C is your limiting constant. F of x is the function that you're trying to find the limit of, and L is the limit itself. Right, so if you want to make a note of that, you can. But it's something that you've been working with for a long time now, so it should be pretty intuitive. This part here is not. Right, so if for every epsilon greater than 0, then there exists a delta greater than 0 such that for all x, we have this condition, this conditional statement, that if x minus c, the absolute value of x minus c, is between 0 and delta, then there must be some corresponding absolute value, f of x minus L, less than epsilon. All right. So that's clear, obvious, understandable. The first time you see it, there's no questions whatsoever, right? Yeah, that doesn't make any sense at all. Yeah, and generally speaking, if you have to ask if it's a joke, you've ruined the joke. You destroyed it. My joke is dead. I mean, I don't know if anybody's religious here, but if you are, say a prayer for my joke. I don't want to do that. Sorry, Jim. So anyway, this diagram should, in theory, make a little bit more sense, but not without a little bit of explanation. Right? What we're talking about are corresponding intervals. Right? So let's focus on the. Let me highlight. Where's my highlighter? Is this a highlighter? All right, so x minus c is less than delta. So let's take a look at that algebraically for a second. X minus c less than, I might have said epsilon, I meant to say delta. All right, the quality of your delta is irrelevant. A lowercase delta. Well, the typed one is a lowercase delta. What I drew is, I don't know, like a music note, I guess. Yeah. Or a Hershey Kiss, yeah. Basically, just make a D with a little tail at the end and you're fine. Right? And in fact, you'll see that later on in the course when we talk about derivatives, that we're supposed to write, instead of dy dx, we're supposed to write lowercase delta y over lowercase delta x, but that's too cumbersome, so everybody just writes dy dx. So that's fine here. Just make it not look like an ordinary d. Just give it a little funk and you'll be all right. Okay, so algebraically, this would boil down to negative delta less than x minus c, which is less than positive delta. All right, so good old algebra 2 coming back. All right, I could also add c to everything to get x alone in the middle. So what this is telling us is that, and this corresponds to the diagram here, it's just this is the absolute value notation, which isn't always clear in terms of what it represents graphically. But when you look at something like this, what we're really getting at is the idea that you have some value c minus or plus some value delta. All right? So what we're creating is an interval around c that is equal to whatever delta is. All right, so an interval around c that's equal to delta. The purpose of which we'll get to in a little bit. right? But that's what this diagram is saying. We have C, we're going minus delta plus delta, and that's creating some kind of interval. All right. Now, for the other one, f of x minus L, you do the same thing, or a similar thing. So that would be, well, I'll rewrite it, f of x minus L less than epsilon.
Mr. Gannon, sorry, I have a question before you move on.
Sure.
I don't understand what you mean when you say that the interval is equal to delta. I thought it was just plus or minus delta. C.
Well, the interval that's around C, that is, well, I tried to shorthand it. It's basically saying that you're going delta units in each direction. So negative epsilon would be less than f of x minus L, which is less than epsilon. All right, in which case we would get L minus epsilon is less than f of x, which is less than L plus epsilon. All right, so it's really the same explanation, except it's an interval instead of being around the C value to be around the L value. All right, so we're talking about, if you look at the diagram, and I'll zoom out so you can see it, we're starting with some value L, decreasing by epsilon, and then we're starting with some value L and increasing by epsilon. All right, so that's what this diagram is really telling us. So let me zoom back in. So it's an interval around L. The sizing is a little off. That is equivalent to epsilon in each direction. And that would be up or down. All right, so these guys are the textbook definitions, the epsilon delta definitions of a limit, but the simplified forms are obviously the ones that would make more sense, because this is really telling the true story, the C minus delta, the L minus epsilon. So I would make a note of that, highlight it, study it, fall in love with it. Etc., etc. They downgraded my highlighter selection, so this is where I'm at. Maybe I'll just use my pointer. So that guy and that guy. There was a way to rotate them at one point. Well, this is knowledge, so I'll use a green lifesaver. Makes more sense. All right, so why? The why is the big question. If you look at the diagram, you're seeing that we're talking about an interval along x that would correspond in some way to the interval along y, right? And so what we can, if we're looking to prove that a limit exists, we just need to prove that there is some relationship between the interval surrounding the C value and the interval surrounding the L value. because what's happening here is as the x values converge on whatever c is, from left and from right, the y value should be converging on whatever L is. And they should be converging in some proportional way, right? We don't really care what that proportionality constant is. We don't care what that rate is. Maybe this one is closing in on C twice as fast as this is closing on L. It really doesn't matter as long as there's some relationship for which the x values converge on C corresponding to the y values converging on L, right? If that exists, then the limit does exist, right? And this is completely unrelated to the act of finding a limit algebraically. That's something that's really important for you to understand, right? So what we're doing is basically, I mean, at this point we'll kind of look at it as a check, but really it's the foundation of something called numerical limits, right? And so computers, they don't understand typically, unless you program them to, they don't typically understand algebra. Right? What they do very well is numerical calculations, and then they approximate the algebra based on their numerical results. Right? So I can find a derivative on Excel. I could find a limit on Excel, but not by saying limit as x approaches infinity of this equals what? Tell me what it equals. It doesn't do it that way. It works with it numerically. So if we can come up with a relationship between the two variables that drives what the limit would be, then the computer would understand how to determine what that limit is, right? And so it actually ends up being guess and check for technology, whereas for us it's an analytic approach. And this is the foundation of that sort of stuff. It would also prove that a limit existed, but for our purposes it's like, well, maybe it's not a proof, but I know that this is correct because if I plug the 4 in, 9 minus 4 is equal to 5, it's a continuous function. I have no reason to doubt that this is going to play out, right? But if I needed the computer, any form of technology to come up with that 5, I can't just type this in, right? I can't just type it into Excel. All those engines, like Wolfram Alpha and stuff like that, they don't work analytically. They work numerically, and then they approximate the answer with some known function. So they look at it and say, I have this numerical relationship. I'm programmed to know that that's a natural log. So I'm going to replace that numerical relationship with natural log and go from there. Right? So that's a lot of abstract stuff, but really we need to carry out this process and then apply it at some point. So let's worry about the how, and then we'll get into more of the why down the line. These are the two guys that I think you want to know. All right, so let's mark this up and see where it takes us. So we have a C value. We have f of x. And we have an L. I mean, it's really plug and chug, at least initially. So the C value is 4. So if I'm working with C minus delta less than x less than C plus delta, I'll just focus on this for now. We're looking at the C value of 4 minus unknown delta less than x independent variable, which is less than 4 plus delta. So then I have the other guy, which is L minus epsilon less than f of x less than L plus epsilon. The L is 5. Epsilon and delta are what we're trying to prove that a relationship exists between. So let's hold that thought. We know what f of x is 9 minus x. 5 plus epsilon. All right, so we have to do a little wiggling with this guy over here, this compound inequality. The one on the left, that's good to go for now. I want to be able to merge these two inequalities, right? So in order to do that, I want to isolate x in the middle so that they have the same structure. So let's do that. I'm going to subtract the 9 first. We're looking at -4 minus epsilon less than negative x less than -4 plus epsilon. Then I'm going to divide everything by -1, which is going to reverse the sign on everything. So epsilon plus 4, or 4 plus epsilon, doesn't matter, greater than x, greater than, I'll do negative, I'll be consistent, negative epsilon plus 4. Probably should have left it the other way, but I didn't, so here I am. All right, so these two guys are inconsistent. I got a less than, I need a greater than, or I have a greater than and need a less than, so you can manipulate it any way you want. Pretty easy to do, just rewrite. Now I'll actually switch the order. So 4 minus epsilon less than x, which is less than 4 plus epsilon. All right, so now it's comparative. Because x is bounded between 4 minus delta and 4 plus delta, but it's also bounded between 4 minus epsilon and 4 plus epsilon. In order for the limit to exist, the lower bounds need to have some relationship and the upper bounds need to have some relationship. And again, some relationship, not a particular relationship. We're not looking for anything definite. We're looking for something that exists as a relationship between epsilon and delta. It does not matter what that relationship is as long as it does in fact exist. All right, so let me just do this. Let me snag the lower bounds and do a quick 4 minus, screwed it up. 4 minus delta is equal to 4 minus epsilon. That's a nice one because that simplifies down to just delta equals epsilon. So we have a relationship. I'll also test the upper bounds. I'll go, let's see, I don't like this color. Let's get in this neck of the woods here. Yeah, that's the one I want. So these two, 4 plus delta equal to 4 plus epsilon, in which case you get delta equals epsilon again. All right, so that equality proves that the limit exists because it proves well, in this case, it's a one-to-one relationship between epsilon and delta. But it could have been delta equals 2 epsilon, it could have been delta equal to half epsilon, delta equals the square root of epsilon. It doesn't matter as long as there's a relationship comparing delta and epsilon.
Why can you assume that two things that are less than x are both equivalent? Just because something's less than x doesn't mean it's the same as everything else that's on the
True, but in order for the limit to exist, that's a principle that has to be in play.
Okay.
I know it's just like one step and takes like 2 seconds, but do you have to show that math to like set them equal to each other? Or can you
Are you
just say,
saying like go right to this from all that stuff?
Well, no, but like without doing like 4 minus delta equals 4 minus epsilon, can you just say that there's a relationship because you can just sort of look at it and see it?
As long as you tell me what the relationship
Okay.
is, yeah. Yeah, you could skip intermediate steps as long as you get to the end game. All right. Now, something to keep in mind, the relationship on the lower bound and the relationship on the upper bound may not be the same, and that's okay. We generally report both of them because you may be approaching at a different rate, or at least a different proportion for x as it's coming from the left and y as it's coming from the bottom, as you are, so that might have one rate compared to x coming from the right and y coming from the top. And that's okay, as long as in either event you're zeroing in on whatever the whatever the limit is supposed to be. And a pretty good example of something like that would be a piecewise function where you have something like this. Let's say a linear function and then something that goes exponential after that. All right, so the rate at which I get to this location, depending on the variables, the rate is going to be much different than it would be if I'm traveling along this line, right? Just based on the properties of the functions, all right? So that's totally understandable, all right? Here, because they're the same, I just need to box one. If they're different, you just box them both and call it a day. I'll know which one you're telling me is the lower bound and relationship and which is the upper bound relationship, because you in theory have done the work to identify that. You set these equal, and then you set those equal, so it's pretty clear. If you skip that step, then just make a note that this is the lower bound relationship or the upper bound relationship or both, right? And then it'll be pretty obvious. Something with a little oomph to it. So again, you got your C, you got your f of x, and you have your L. All right. So, you know, at least until you get comfortable with this, you might refer to the rules. But when you are comfortable, you probably shouldn't need to. But anyway, we're looking at 1 minus delta less than x less than 1 plus delta. All right, that's the C minus delta, C plus delta. And then 1 minus epsilon is less than f of x minus L, so 1 over x. Right, so 1 over x, and then 1 plus epsilon. Evidence gone. All right, so the 1 minus delta business, that's all taken care of. We don't have to worry about that. We do have to take care of the other guy, though. So we need an x in the middle. So we're going to do a flip-a-rooski on everything. All right, so within a compound inequality, you can flip your fraction. You just got to flip everything else too. Right? And the reason why you're flipping the inequality signs, I mean, you can just remember that you're flipping everything, but that's not really telling you anything. Is that it's the size relationship is now different, right? So if I have this relationship, that's true enough because I'm subtracting something from one, I'm adding something to one. So that size relationship makes sense. But when you flip it, here you're taking one and dividing it by something smaller than you are here. So if you divide one by something smaller, it's going to be a bigger number than this one. So that would change our inequalities to make a true statement. All right. But then we also want to switch it around to make it consistent with the other compound inequality. So 1 over 1 minus epsilon less than x less than 1 over 1, I'm sorry, plus than 1 minus. All right, so complete changearoo there. All right, so I'll set my lower bounds equal. LB for lower bound if you want. If you don't like that, then whatever, you're just not a team player. That was also a joke. It wasn't a good one, though. Now, you can come up with any way of designating it if you want. It really doesn't make a difference. Just some way of indicating. LB is fine for me. It changes from year to year what's fine for the College Board. My belief is that nothing is ever fine for them. So, you know, just get in the habit of writing out complete thoughts, and when you have a complete thought, elaborate on your complete thought to make it complete, or I don't know, complete plus, just because they tend to be terrible people. So anyway, I'm going to solve this for delta to really illustrate that relationship. So subtract the 1. And divide. And you get a relationship. We needed a relationship. That's good. However, this relationship is not always true. That's a semicolon. It always looks like a J and people complain, so. Epsilon can't be equal to what? -1, otherwise it's undefined. All right, now, so you'd say, well, that's not proving a relationship between epsilon and delta, so it failed. This is not true, right? But if you look at the calculation, you plug in a 1, 1 over 1 is equal to 1. Common sense is telling us it is true. There's a very good reason why this is completely irrelevant.
Yeah, I was going to ask on the other page, I was going to say that they're both greater than 0.
They're both greater than 0, yeah. So there's that component, and there's also the fact that it needs to only exist for small values, right? So if I have something, let's say, epsilon unequal to 2. Let's say I had 2 minus epsilon on the bottom here. So you would say 2 is a bad number. So it destroys the whole thing. And not true, because you need to prove that there's a relationship, but the idea is to show that for incremental changes around your C value and your L value, that it really exists. So it really doesn't matter for large values, it's really only for small values. But in this case, it's irrelevant because you can only have non-negative numbers anyway. All right, so then we figure out the upper bound, the UB. One plus delta. I don't know why I had to look at that, but I did. So delta would be equal to, well, this one is going to be negative 1 plus 1 over 1 minus epsilon, where epsilon cannot be equal to 1. In this case, we have a positive number, but it's a relatively large positive number, so it doesn't make a difference anyway. And again, the idea is that we're looking at cases where it's kind of a limit within a limit, where we want to find basically what would happen if you were to minimize what the epsilon and delta values were. So if I were to find the limit of this as epsilon approaches 0, what would that give me as a delta? If I were to find the limit as delta approaches 0, what would that give me as an epsilon? In both of these cases, we get something that actually exists, so we're good to go. And really, that's all we need. The only time that we're looking at something that's going to fail, and this is the good news if you're worried about just getting stuff right, if you get a cancellation of one or both of the variables. Right? If epsilon or delta cancel out through the process, then, well, either you screwed up, which is not likely, or the limit does not exist. That being said, you should probably know whether the limit exists or not based on the problem itself. Right? So you look at this and say, I plug in a 1, I get a 1. I plug in a 9, I get root 4, which is equal to 2. But then you might look at this one and say, well, wait a minute, it could be a -2 because it's plus or minus. That's not true in this case because you're not providing the radical, so keep that in mind. If the radical's already there, the sign of your answer is whatever the radical sign is. If you're putting the radical in, if you're the one actively taking the root, then you have to worry about the plus or minus stuff, right? So don't get tripped up by that. But that's the kind of situation where you might run into a problem where you have maybe some undefined component of the radical or fraction or trig function or something like that that throws you for a loop. But if anything with rational functions or polynomial functions or anything like that, if it works in the limit problem, then you should get some discernible relationship between epsilon and delta through this process. And if you don't, then we talk and we figure it out. All right, so you're going to do for homework, classwork homework, numbers 3 and 4. And time is it? 39. 39? So did my message come out yet?
Yeah.
Okay, cool. So end that problem.